So we're here at ARM, here at Computex. So who are you?
I'm James Bruce and I'm ARM's lead mobile strategist. And one of the interesting things that we've been talking about at Computex this year is the Cortex-A12. And this is a part of a launch for mid-range smartphones. So the key thing about the Cortex-A12 is that it's been designed to be a follow-on to the Cortex-A9. What we're seeing is incredibly strong growth in the mid-tier smartphone market, and the Cortex-A9 has been very successful there. But what we're seeing is that consumers are demanding more from their smartphones. They're in a situation perhaps where they don't get the high subsidies, or they just don't want to spend $600 on a smartphone, but they still want those features at a sort of $300 price point. And what the Cortex-A12 does is it delivers the latest features such as virtualization, big.LITTLE, and a 40% performance increase over the Cortex-A12. So it's a perfect solution for mid-tier because it also keeps the power and price within that of the Cortex-A9 that you see on handsets today.
So how is it compatible with the A15?
So it's got exactly the same features as the Cortex-A15, so it's got the large physical addressing, so you can address more than 4 gigabytes of memory. It's got the virtualization, so you can do bring your own device technology on it. And it also supports big.LITTLE, so it's, you can actually put a Cortex-A7 on there, or a cluster of Cortex-A7s, to get really low power for those low performance tasks.
So all the big.LITTLE software development that's happening is fully compatible with A12?
Absolutely, yeah, absolutely compatible.
Fully
compatible.
Not even some changes or something that needs
well,
to be
there's always, I mean, from one SoC to another, there's always small changes, but beyond the normal BSPs, there's no changes required.
And how is the compatibility with A9?
So all the great applications that you have on the Cortex-A9 today will run just as well on the Cortex-A12, just as well as applications that on the A9 will run on the Cortex-A15 or on the Cortex-A7.
So what is there's a physical difference in size of the chip, right?
Absolutely. If you actually look at the mid-tier market, or if you look at smartphones generally, life is great at the very high-end smartphones because you can just use the most, a large SoC, there's no cost constraints, you just put the best technology down. When you look at mid-tier or entry-level smartphones, you run into the challenge that you are cost constrained, and if you try and bring in a high-end part into these lower cost points, it means that the overall user experience of the handset will be compromised, because then you've got to cut costs on screen, memory, the actual mechanics. So what you see is that, for example, if you look at a high-end SoC, that normally has a size of around about 100 millimeters squared. A mid-tier part is 60 millimeters squared, and an entry-level part is probably about 40 millimeters squared. So really what this allows you to do is, with the Cortex-A12, is deliver that the right sort of balance between sort of performance and cost at this sort of 60 millimeters squared price point.
That's ARM's core business what's called strength, is to figure out the balances, right?
Absolutely, and I mean that's why you see everything from the Cortex-A7 to the A12 to the A15 is really offering CPUs at the right price point for the given needs of the market.
So, was that planned like years ahead, but only being announced now? How does it work? Because you had the idea, I guess, like 9 and 15, there would be space for something in between, right?
It's a classic case we had the idea, but it's all about engineering resources. ARM's been very busy. We've had the Cortex-A53, the A57, plus the A15 and the A7. And also, it actually worked out really well, because what we've seen is that the mid-tier market's actually been quite small up until recently, but we're seeing a lot stronger growth. So what you'll see is over the next year, a few years, the mid-tier market will actually grow to about 400 million units by itself.
Per year?
Per year.
Just the mid-tier?
Just in the mid-tier.
That means there's top and there's bottom.
That's right, yeah, exactly.
Smartphones? In
smartphones. I mean, if you look at in 2013, you're already going to probably see about 1 billion smartphones being shipped. So you can definitely see how, as smartphones at the entry level replace feature phones, how over the next few years the growth of the smartphones is just going to increase.
Is it possible to say then that A7 is 40 millimeters squared, A12 is 60 millimeters squared, and A15 is 100 millimeters squared?
I definitely would never say that, and the reason for that is that we're talking about the SoC here. So when you talk about, for example, the 60 millimeters squared, that's also including things like the graphics, the video, the modem, perhaps you're going to see Bluetooth, Wi-Fi integrated. So it is a system on chip rather than just a CPU. The actual size of the CPU in that overall 60 millimeters is incredibly small.
Incredibly small.
Yeah.
So the SoC looks like a black piece on the PCB, right?
That's right. Yeah, yeah. It's the black sort of chip. With perhaps ARM written on it and the silicon partner's name written on it. And I mean, just to give you a sort of idea of size of the cores, if you look at the Cortex-A7, which has been used in entry-level smartphones, the size of the actual A7 itself is about the size of a full stop in 28 nanometers. It's half a millimeter squared.
Half a millimeter squared? Is that the ARM CPU?
That's just the ARM CPU. Yeah, so that shows how small the actual ARM CPU is. And also, I think it also emphasizes how important our silicon partners are, because it's not just the CPU or the GPU or the video, it's also all the other stuff that they're actually putting around the processor to actually build a complete system on chip.
But that sounds tiny.
That's
half
the whole
a millimeter squared.
Half a millimeter.
That's what the ARM CPU is on the A7.
On the Cortex-A7, it's half a millimeter squared.
Where is it? Is it just in one place, or is it spread out, or?
No, it's normally in one place. So, for example, if you've got quad core, you have 1 millimeter squared of the A7, but the whole idea is to get that sort of really low power efficiency, that really low cost. That's where a part like the Cortex-A7 comes in.
And it's doing a good job right now, getting the low cost.
Absolutely, yeah. There's some great phones being launched by MediaTek, based on MediaTek, and also you saw today that Qualcomm announced a LTE part using the quad-core Cortex-A7, so there's a lot of market momentum.
And how about A5, A8, A9, what's going on? How do this, like all these different...
So you still see A5 and A8 shipping in the market, but what you're seeing is, for example, the A8 was replaced by the A9, and the A5 is in the process of being replaced by the A7. I think it's very much, if you look at the ARM philosophy, it's always about doing more with less. And each generation we try and deliver more performance, better power efficiency, better size efficiency compared to the previous generation.
And A12 is just going to be 28 nanometer and smaller?
You could technically put it in 40 nanometers, but what you see is that the right price point for our silicon partners at that point in time will be 28 nanometers.
And it's all synchronized in time, like they just kind of shipping the 28, well, they've been shipping for a while, but the price points and everything and the yields are going to be perfect when it launches.
Oh, absolutely. But even today you see Cortex-A7 sort of entry-level parts shipping in 28 nanometers. So what you're really going to see is over time, 28 nanometers hanging around for a long time just because it's so cost effective. And that's where the size of the ARM core is coming yet again, because it allows the silicon partners to stay on the most cost-effective process.
And so there will be 22 for A58 maybe, or what they was talking about, the TSMC test chip and all that?
That's right, yeah. So, I mean, you'll see, for example, 20 nanometer being used for Cortex-A15 and Cortex-A57, and also you'll see 16 nanometer FinFET and 14 nanometer FinFET being used for A57 and Cortex-A15 as well.
But they can all be in any size?
They could be in any size. So if you wanted to do it in 180 nanometers, you could do it.
Are you talking smartphones only, or it could be tablets, laptops, or
other absolutely. Things? And I think that's the important thing to emphasize is that if you look at these SoCs now, they're spanning many form factors, and our silicon partners are reusing their IP to address particular market needs. So it could be anything from a smartphone, tablet, or form factors that we haven't even thought of.
And do you consider Android when you design a chip, or that's just like it just automatically gets developed, all these things?
So what we have a very close relationship with a wide range of software companies, and we make sure that when we're designing an SoC, it will run these multiple OSs very well. Because I mean, you've got to think, if you look at the Cortex-A9, that was actually designed in 2005, 2006. And a lot of this mobile revolution that we've just seen in the last few years wasn't even thought about when we were designing the Cortex-A9. But we talked very closely to software companies, and we ensured that the Cortex-A9 was ready when the sort of mobile software ecosystem came upon us.
So it has to happen that there needs to be those months or year or something before it comes out. That's necessary. You can't just like release it 6 months from now.
That's right. Yeah. I mean, that's right. Because when we announce a part, we've already designed it. It's already gone through initial verification and testing. But the actual sort of, from should we say, the paper design to actual shipping of a handset can easily be 5 years.
Right, but this is planned for 2014?
End of 2014, early 2015, you'll see handset shipping with this part.